Hi guys, so a lot of my students have been struggling with statics of rigid bodies, dealing with frictional force and also moments. So I'm making a short little video about going through how to go through this type of question. I've labeled a 4-step process here, and I'd recommend you use this on all 4 of these questions. So first we're going to focus on realizing and labeling all the forces, and also realizing why we're using these 3 equations. It's told you there's a uniform rod. Uniform means that all the weight acts at the center. So what you'll notice is that while I'm going through this question, I'm labeling all the key information that this gives. Now, the weight is equal to mass times g, and it's told you that the rod is 6 meters long, meaning that 3 meters along the rod, so let's label a distance of 3 meters, there's the weight that acts at the center of the rod, and that's equal to the mass of 10 multiplied by acceleration due to gravity, g. It's told you that it's in equilibrium, and the fact that it's in equilibrium, that's what tells you that you can use the fact that resultant velocity is 0 vertically, the fact that it's 0 horizontally, and the fact that clockwise and anti-clockwise moments are equal. That's what tells us. It's told you that A, where it rests, is on a rough horizontal ground. Let's think about if it wasn't at rest. What position would this rod move in? Well, it would move to the left, wouldn't it? Meaning that friction, if it would act to the right. Now, what is friction equal to? Well, friction, I'm just going to write F, but I'll just write out friction, is equal to the coefficient of friction, which is actually what we're trying to find here, multiplied by the reaction force where the friction is acting. I'm going to call that reaction force at A, and I'll tell you why in a little while. So, straight off the bat, that's another force actually, the reaction force at A. Whenever 2 objects make contact, like here the rod is making contact with this surface, there's always a reaction force that's perpendicular to the surface. And now this frictional force is equal to mu, which we don't know, multiplied by the reaction force where it acts, so Ra. Are there any other forces? So it tells you the rod is resting on a smooth peg at C. The fact that it uses the word smooth means there's no friction at the position of C, even though there's contact. However, there is still contact, meaning there would be a reaction force at C, and it would be perpendicular to the surface. Let's call it RC. It says AC is equal to 4 meters. Let's label that in a different color because it's getting a little bit messy. So AC is this distance here, and that distance is 4 meters. It says the angle between AB and the ground is theta, where tan theta is 0.4. Now, you can use that to find the value of theta, and yeah, we might as well, just to show you like this method. So if I put in my calculator inverse tan, by the way, I am in radians mode, in degrees mode. So inverse tan of 0.4 is equal to 21.8 degrees. We can use that now to find cos of theta and sine of theta by just substituting that into sine theta or cos theta. It says given the rod is on the point of slipping, so once again it's still in equilibrium, meaning we can apply all 3 of these equations. Find the coefficient of friction. Okay, so what has that been? 2-3 minutes, and we haven't even started on the question. This is what tells you in mechanics the most important thing is laying everything out. Now that we've done it, we can employ all these rules. So resultant force is 0 vertically. That means that all the upward forces, so what are the upward forces? There's the reaction force at A. What else are the upward forces? Well, this is strictly horizontal, so it has no vertical component. This is the downward force. We have to be very careful because this reaction force at C actually has a component that acts vertically upwards. So how do we find that? Well, if we draw it out the other way, we know that this angle here is going to be equal to this angle theta, and we can draw out that triangle a little bit larger, just like I've done here. So this hypotenuse would represent RC. We know this angle is theta, and we want to find the vertical component because we want to add the vertical forces upwards and make them equal to the vertical forces downwards. So how do we find that vertical component? Let's call it Y. Well, we can use SOHCAHTOA because it's a right angle triangle. We're not interested in the opposite. We're interested in the hypotenuse and the adjacent. So we can say cos of the angle theta is equal to the adjacent of y divided by the hypotenuse of the reaction force at C. We can rearrange that to get y is equal to RC cos theta, and that's the vertically upward component. So we can say RA plus RC cos theta is equal to the downward component, which is the weight 10g. You can go further here because you can find cos of 21.8. So we might as well do that. So RA plus, I'm just going to put this into calculator, cos of 21.8 gives you 0.928. So let's write 0. I would round to a few significant figures here because when you round in the middle of the question, it does end up affecting your final answers. So being as accurate as possible would be useful. That's as far as you can go using resultant force is 0 vertically. So let's move on to the next step. Let's use resultant force equals 0 vertically. horizontally. You might be a little bit stuck on what to do now, but once you form the three expressions, you'll see how they play into effect together. So what are the horizontal forces? There's this force of friction acting to the right, mu Ra. Are there any other forces acting to the right? No, actually. No, there isn't. This is strictly vertical. This is strictly vertical. This does have a horizontal component, this component here, but that's acting to the left. So we say the force acting to the right, friction, is equal to the force acting on the left, which is the horizontal component of this reaction force at C, which is like this here. So again, let's use this right angle triangle, this amplifying X. I'm going to change pen color because it's getting a little bit messy. So we want to find X. We know for sure this is the reaction force at C. So this time we're going to use the opposite and the adjacent. What's that involved? That's the sine equation. So we can say sine of the angle theta is equal to the opposite, which we're trying to find. Let's call it X, all divided by the hypotenuse RC. You can multiply both sides by RC and get RC sine theta is equal to the horizontal component to the left. So what we can do now is we can replace it with RC sine theta. We're almost at a stage now where we can find the coefficient of friction. We just need to find a few other things. Well, actually, we can find sine of theta, can't we? Because we know theta is 21.8. So let's do that. Sine of 21.8 is equal to 0.371. So we can say it's 0.371 RC. Okay, we've now got two equations with RA and RC. If we find RA and find RC, we can easily put it into this equation to find the coefficient of friction. But we don't yet have enough variables. We still have one more equation to substitute into, and you'll see how it all plays into effect once we substitute into that. What I'm going to do is I'm going to erase some of this working out here just so I can fit the question in with the working out. Okay, so moving on. Where would you take moments about? What do you think? Would you take it about A, about this position, or C? I'd recommend taking it about A, because where you take the moment from, you don't need to take into account the force or the moment created by the forces acting at that point, because moment is force times distance from the pivot. But these forces have no distance from the pivot. So we don't need to take into account the moment about RA and the friction. So let's take moments about A. About A just means you're using A as your pivot. You'd say, but one thing you have to be careful of actually is the force that you take, you can't take 10g and multiply it by 3 because 10g is not perpendicular to the surface. You have to take the component of 10g that's perpendicular to the surface. So I've drawn this out. This angle theta matches with this angle here. And you want to find this vertical component. So let's draw this triangle out now. We have the hypotenuse of the triangle is 10g. We have this angle here is theta. And we want to find this component here. Let's call it y. We're not using the opposite. We are using the quadruple, by the way, and we're using the hypotenuse and the adjacent. So that's cos. Cos of the angle theta is equal to the adjacent, which is y, divided by the hypotenuse of 10g. From there, you can multiply both sides by 10g and get y is equal to 10g cos theta. So now that we've got the force, we can take the force that's perpendicular to the surface, multiplied by the distance from that force. So that's 3. By the way, this would create a clockwise moment, because if you were to turn it in the direction and apply the force here with the pivot IA, it would turn it in that direction, in the direction of a clock. So I'm just going to make a little note of that clockwise moment. However, this force here, if you were to turn it using A as a pivot, you'd see that it turns anti-clockwise. So that's the anti-clockwise moment. This force RC is already perpendicular to the surface, so we don't need to take into account components here. We can just take the force directly and multiply it by it, from it, the distance from the pivot. So that's 4. And because we know theta, we know g, we're able to solve this for RC. So let's do that. RC is equal to 10g times cos. So you can even replace g with 9.8 if you'd like. Times cos of the angle that we introduced before, 21.8. All multiplied by 3, all divided by 4. So let's do that. We have 10 times 9.8 times cos of 21.8 times 3, all divided by 4. And that's equal to 68.2. Okay then, now that we've got RC 68.2, we can use that. Let's talk about how to use it now. So, still a few difficult things to do, but hopefully you guys are seeing how everything ties in together. Now that we've got this, we can put into this equation. We can say mu times RA is equal to 0.371 multiplied by the value that we just found, 68.2. So let's multiply those together. And you get that mu RA is equal to 0.371. Again, this is very difficult, so if you do need to rewind, just let me know. I mean, not let me know, you can rewind. We're almost there now. We just need to find the reaction force at A. And if we look at this equation here, we can rearrange this for the reaction force at A. Because we know it's 10G, take away all of this. 10G, take away 0.928 RC. And we also know RC is 68.2. So that's 10 times, well, G, which is 9.8, take away 0.928 multiplied by RC, which is 68.2. And what's that equal to? I'll check right now. So we have 10 times G, take away 0.928 multiplied by 68.2 is equal to 34.7. And there you go, we're nearly at the end now. We can now replace the reaction force at A with 34.7. So 34.7 mu is equal to 25.32, and divide both sides by 34.7, and you'll get your coefficient of friction. So in this case, that's 25.32 divided by the answer that we just got is 0.729. Or let's say 0.73. That's your final answer. Again, a whirlwind of a question, but hopefully you guys can see that when you form these three expressions, when an object is in equilibrium, you will be able to rearrange, find specific variables, put one equation into the other, and get to your answer in all of these questions. Thanks for watching. I hope this video helped. If you have any tutoring inquiries, be sure to visit my website www.excellineducation.co.uk. It's on the first link in the description too.